All right, I'm starting the stream. Oh, great. It says excellent condition. Let's see. All right. I realize nobody's here yet, but I'm going to tweet about this really quickly. All right. And I think I will also share this on Facebook. Okay. All right, well, we're back here for the last day of the workshop. I expect people to kind of trickle in slowly because I unfortunately had to start a little bit late because of an appointment, and but I'm here and I'm ready to get started. Now, my internet where I currently am is not as good as my normal internet, but hopefully that won't be a problem. You can see here, in fact, that my streaming setup is quite different. I'm streaming from my laptop, and here I'm using 20% of my CPU just to stream, whereas at home I am normally using like 2%. So if the quality doesn't seem that great, I really apologize for that, and worst case scenario, we will try to redo this tomorrow. But I really don't think that'll be necessary. I think we should be able to just continue from where we left off yesterday. The other disadvantage I have right now is that I don't have dual monitors, so I'm gonna have to shuffle everything around and hopefully not lose track of chat, but we'll see what happens. I think I'll give people another moment to get here, just to be courteous. I expect that will actually affect the numbers pretty significantly. But let me take a look here. And I think, I may as well go ahead and get started. So welcome back. Today we're going to continue the discussion from where we were last time when we were talking about the Natural Language Toolkit. And you can see my screen here. I'm showing the terminal, the code, and then my screen here at the bottom. I hope this isn't too small. As I said, worst case scenario, I can re-record this stuff tomorrow, but hopefully that won't really be necessary. So we finished off last time with a dispersion plot where we looked at incidents of specific terms that come from the Sherlock Holmes stories. And in this case, we're looking at Holmes and Watson, just to kind of see where do these characters get mentioned across the whole text. Now, the Natural Language Toolkit does come with a number of other extra features that make it really handy to use. And I'll go ahead and just show those really quickly so you can get a sense for them. And then I want to move on and talk about actually building a pipeline to do our analysis. Okay, and so we're going to wrap up today, and I will go ahead and go all the way, I think, to 3:15. I don't think there's any reason to cut it off any earlier than I need to. You know what? I've been talking to myself because this is a private video. Technical snafus. Visibility, public. Done. Save. Okay, hopefully. I was wondering, why is nobody showing up? I figured it was because I was starting late, but it turns out I was private. Hopefully that'll fix it. Yep. YouTube says the video is not available because it's private. Yep. I fixed that. Hopefully hopefully that fixes it and folks will be able to come on over. So I guess I have to start over. Okay, let me make sure. All right. Okay, it looks like people are able to join in now, which is great. Yeah, I'm really sorry about that. I'm actually not streaming from my normal setup here because I had to be. I had an appointment that I had to get to this afternoon, and so that's why we're starting about 20 minutes late. And I am streaming from my laptop, and so I do apologize if the audio quality isn't quite where it could be, or if the stream quality isn't as good as it has been. And so the format's going to look a little bit different, where I have my code up here, I have the terminal, and then you can hopefully see me. And hopefully this will work out just fine. I mentioned this already, but it turns out the video was private. I'm using a lot of my CPU to just stream, so this might kind of bog down my code a little bit when I try to run it. Hopefully that won't be an issue, but we will see what happens. So I think may as well go ahead and get started. We're going to start by talking about a few more of the features of the Natural Language Toolkit. So right now I have pulled up for you here the NLTK demo that we were working on yesterday. And so we had finished off by looking at this dispersion plot where we're looking at the different frequencies of terms in the text. So in this case, we're looking at Holmes and we're looking at Watson. But there are a lot of ways we can improve this kind of analysis. You know, we could think about things like capitalization, we could think about conjugation. There are all sorts of different things we should be thinking about as we're trying to make this code run well and do interesting analysis. I can actually see that my bit rate is wavering a little bit, so hopefully my internet connection here is not going to cause us any problems. I said earlier it might be necessary to retry this tomorrow. I hope it doesn't come to that. I think we can push through and get some cool stuff done today, because I have what I hope are kind of exciting plans for building a pipeline that you can use to visualize term frequencies across multiple documents. And you can search for these terms and, you know, visualize them. So, and we'll do that for English, we'll do it for Chinese, and we will also do it for French. Okay? So let's talk about a few extra features that exist in the Natural Language Toolkit that you can use to push what you're doing a little bit further than what we have already talked about. And I have my notes here, and I'm going to try to make it so they don't cover up chat, but I can still see my code at the same time. This is going to be a little tricky, but we'll see how it goes. All right, I think I can still see chat, and I can see my notes, I can see the code. I think we're good to go. So there are a bunch of different functions that come along with this NLTK text object. And so you can see that I've highlighted NLTK.text. This is one of the big objects that the Natural Language Toolkit provides us with as kind of a convenience. Now, a lot of the things that it does, we could write pure Python to do for ourselves, but the advantage of using NLTK or some other library like it is we don't have to write all of that code ourselves. We can just depend on the experts. And that's a really good thing, because it's often not worth the time to reinvent the wheel. We don't really want to be doing that. We walk through a lot of these steps to get here because it's necessary to understand the syntax, it's necessary to understand the building blocks, but once you have a feel for that, we can start to turbocharge this a little bit. We can rely on other people's code a little bit more. And one of the things we're really going to rely on are tokenizers, because it is a complex process and it can be difficult, particularly as a layperson who doesn't necessarily specialize in linguistics, to know what constitutes a word and how can we transform a big chunk of text into individual words. So we're going to take advantage of these libraries to do that. So I'm going to comment out this term here. And I don't want to actually run this dispersion plot for the moment, but you should know that it exists. The next thing I want to show you how to do is to look at collocation. So these are words that tend to appear next to each other in a particular document. And so here I can, from this NLTK text object, take my document and I can just call the collocations method. And this will print out words that often appear together within these documents. And I'm going to double check my OBS to make sure that you can see that. I think you can. Hopefully that's fine. And now I'll run this over here on my terminal. You'll notice that I'm on a Mac here because my laptop is a Mac. And I realize it's best practice to always stay on the same computer so it doesn't introduce confusion. But life sometimes gets in the way. So I'm going to change my directory to my desktop to this from 0 to n folder. Okay, and I was doing this on the Windows machine. It's exactly the same. Here I'm going to say ls just to check what's all in this directory. And we can see that I just have all of the same things that I had from yesterday, including, in this case, the nltk.py file. And so, excuse me, nltk_demo.py. As I said last time, don't just name it nltk.py. So I'm going to run that, nltk_demo.py, and what it'll do is it will load in this text, and then it will find the collocations, so words that appear together. And so in this particular case, Sherlock Holmes, that's not really a surprise. Said Holmes, not really a surprise either. St. Simon, Mr. Holmes, St. Clair, Baker Street, Lord Street, Young Lady, Irene Adler, Miss Hunter, and so on and so forth. So that can be kind of a handy thing to do when you want to explore some of the linguistic tendencies in a document that you're working with. Now, NLTK does have a corpus object as well, where you can input multiple texts. I'm going to save that for a future stream because I'd rather show you kind of the process of building a customized pipeline to do some analysis instead. But that is one handy function of the Natural Language Toolkit. It also has an object that is known as a frequency distribution object. So one thing we can do is I'll comment this out, and I can say, let's get word frequencies. And here we can give it either the NLTK text object, or we can give it just a string of words. That doesn't matter. And so if we've already tokenized, for example, a Chinese document, we can use that. So I'm just going to save this in frequencies variable that I am choosing to name that, and then I'm going to call nltk.freqdist, and then I'll give it my document. And so what this will do is this will essentially go through and do what we were doing yesterday and count up all the words, but it'll give us a lot of convenience functions to quickly interrogate the frequency distribution of our words. So, for example, I can print out the frequencies, and this acts just like a dictionary. So in order to access an object out of this frequencies object, this frequency distribution object, I use square bracket notation, and then I can give it the term that I'm interested in. So for example, if I want to know how often is and used in this text, all I need to do is give it that, I run it, and it will load it in, do the frequency distribution, and then we can see that and is used 2,801 times. And of course, we can look up other words. We could look up homes if we wanted to. And I didn't check if I can do this, but we might be able to give it a list of terms. I don't know for sure if this will work, but we're about to find out. We're experimenting together. If it won't work, it'll just give me an error. Yeah, it doesn't like that. So it only wants you to interrogate one word at a time. That's fine. Just keep that in mind. You can probably tell that I don't often use NLTK in the course of my research because it doesn't have a lot of functionality for Chinese. But it's still extremely useful. We can, however, get things like the most common words. So for example, if instead of getting the frequencies for homes, maybe I want to see the 10 most common words. Frequencies dot most common. And then inside parentheses, and here I'll take this print statement away so you can see this a little bit better. And I'll just say most common equals frequencies dot most common. So this is a method associated with this frequency distribution object that goes in and finds what are the most common words. And we can give it a number, let's say 10, and this will give us the 10 most common words, which I will now print. So printing most common. And apologies if you can hear my computer's fan. It's really spinning up right now. Disadvantage again of using these streaming from a laptop. And so here you can actually see the 10 most common words, as I said. So we have commas. There are 7,652. It actually kind of surprises me that there are so many more commas than periods. But whatever, that's not necessarily a big deal. And so, that is what it is. Now, we can also see the words that only occur once, if that's something that we're interested in. And we can do that with frequencies dot hapaxes. So hapax, and I can never remember this word, it's a Latin word, hapax legolemens or something like that, just means words that only occur a single time in a corpus. And we can print this and it'll just give us all of the words that only occur once in our document. And this can be a useful thing for, learning a little bit about some of the semantic content of a text and these sorts of things. And here we can see we have all of these words, chapter. A little bit surprising that chapter only occurs once in this text. Rearing, boiling, pitiful, attractions. So, that's sometimes we learn interesting and unexpected things from these documents. So I'm going to clear this off. As far as this most common object or this most common variable, if one thing I did want to say about it that I neglected to say is the format that it returns to you is a list, but inside that list you have tuples. So tuples are objects that we have not talked about yet, but they are immutable. That means you can't change them. And they function similarly to lists, except that you can't change them. And so a lot of programs will use them to return information to you. And in this case, the first item is the word, and the second item is the number. So if we wanted to access these, for example, we could print common 0. And so if we print common 0, then it's just going to show us comma 7,652. Right? But if we wanted to go further into this and access either the comma or the 0, we can address the index of this tuple directly. So 0 for the comma, 1 for 7,652. So if I add this square bracket here and say 1, it will print out 7,652. And so you can see that right here. So 7,652. So that's kind of how you go in and access this nested information inside this list. So that, I think that wraps it up for a lot of the text object analysis, but I do want to show you how to refine this a little bit more. Because when we were looking at this, we're seeing commas, we're seeing periods, we're not accounting for upper or lowercase letters, and we're not stemming or lemmatizing. So let me show you how to do that. So I think I'll just continue, excuse me, I'll continue to edit this file, and I will save it as a new one. So I'll just save this as NLTK demo _2. And what is the over/under on me remembering to run _2? We'll see. We'll see. I'll probably wonder why it doesn't work, and then realize it's because I'm running the wrong file. Regardless, let's refine this. I'm going to go ahead and get rid of. Well, no, I'll just comment this stuff out down here at the bottom. Okay. So one thing that I might want to do is I might want to remove words that are not interesting to me. So this might be stop words, this might be punctuation, whatever. And I think I mentioned this briefly last time, but we will we'll re-emphasize it now. So I'm going back into my code in between the words tokenization process and the creating the text object. I want to play around with this word list. So something I might want to do is I might want to make everything lowercase, and I might want to filter out punctuation. So one way to do this is I can make a new list that I'm going to call filtered words. I'll make it an empty list, and then I'll say for word in words. So I'm iterating with the for loop across the words list. I'll check if word is alphanumeric, so this will get rid of those punctuation marks. And then I'll append the word as lowercase to filtered words. So filtered words dot append, word dot lower with parentheses. Now there are some optimizations we can make with this, and then instead of creating this text object with words, I want to create it with filtered words. Now, one thing I often think about as I am writing code for my research is how long is this going to take to run, and are there things I can do to make this go faster? Now, in most cases like this, the scale of what we're doing is small enough that it's not really going to be a hiccup. But when we start to get to the order of tens of thousands or hundreds of thousands of documents, then it can influence it a little bit, particularly if we're doing something egregious as running multiple nested loops. So that's something we want to be a little bit careful about. But this process here is going to be relatively quick. But one way to, speed this up a little bit, and here I'm just going to actually skip the sentence tokenization because I don't really care about that. I could just say up here on around line 8, text equals text.lower, because this will make the entire string lowercase, and then I don't need to do lower here. Because in this case, we're calling lower on every single string or every single word in the text. Here we're just running it once. So, marginal sorts of optimizations are often worth thinking about. So if I rerun this and I print the 10 most common terms, now we're not going to see those punctuation marks in our list anymore. So that can be kind of a handy thing to do if you don't really care about, see, I ran the wrong file. Python NLTK demo _2.py. Someday I'll learn that I shouldn't do that. And I need to print most common. So I'm going to go ahead and just print this whole list, just like this. And now we can see we have the, I, and, to, of, and so on. So this is, again, a refinement on what we had before. Now we also might say, hey, I'm not interested in the, I, and, to, of. These are stop words. Of course, these are the most common words. Maybe I want to delete those. Now, this is a process that is known as getting rid of stop words. And NLTK does have an English stop word list, but I don't remember how to do it, so I'm going to Google this really quick. NLTK English stop words. And all we need to do here is to grab it. Let me see here. I think it's just like nltk.stopwords or something along those lines. Right, here it is. So at the top of our script, we're just going to import stop words. This is another thing that I, generally speaking, don't do. And then we're going to grab English stop words from this list. So here on line 7, I'll say my stop words equals stop words dot words English. I believe that is how this works. And I will just print these stop words so you can see what they look like. My stop words. And let me pull my chat back up just to make sure there aren't any questions. It looks good for the moment. All right, so let's run this. Let's see what this does. When I run this, it should print out all of these stop words, right? I, me, my, myself, we, our, ours, ourselves. You know, this works fine. I'll clear this off. So now we know we have this list of words. So if we want to filter these words out of our analysis, down here in this loop, while we are going through all of these different words and we're checking if they're alphanumeric, we can also say, and word not in my stop words. Oops, my stop words. And so what happens here is we're only appending a term to this filtered words list as long as this statement is true. And so the first statement is this alphanumeric? If it is, that's true. But this also has to be true. And here we're saying, is this word in my stop words? And if the answer is no, then this is true. And so then the whole statement is true. So it just filters out punctuation and stop words. And this is something, the language, of course, we can grab. I think there's a French stop word list. There's probably a Chinese stop word list. And you can, I think, hopefully easily figure out how to do this for the language that interests you. And so let's go ahead and run this code again. So Python NLTK demo _2.py. And I'm still printing this. But now we can see that the top terms are said, upon, Holmes, won, would, man, could, little, see, and may. So now we have refined our process just a little bit more. Right? Now we're not getting tripped up on capitalization, and we're not looking at those stop words anymore or punctuation marks. One thing, let me take that print statement out so we're not printing my stop words. One thing I should point out, however, is line 19 to 22. We can do this in a single line. I could say filtered words simply inside of a list comprehension. I can say word for word in words if word dot is alnum and word not in my stop words. And I believe this should work just fine. Let's comment this out and just make sure that it works. Sometimes when you start to add complicated or slightly more complicated booleans, it can get tripped up, but no, it looks like it worked just fine. So now we're filtering out our words in this process. And often when we want to do any sort of process on every single word in a document, we're going to want to do it in a way where we don't need to iterate through our text multiple times. If we can do it all in one shot, that's really what we want. That's all what we really want to try to do. So what might be the next innovation here? Well, one thing we can do, actually, let's step back here and talk very, very quickly about what we can do with this filtered words list. We can actually, at this point, calculate what is known as the lexical diversity of this text. Sometimes this is an interesting piece of information and sometimes it's not. But the lexical diversity is just the ratio of unique words to total number of words in a text, right? And to check this, we would generally not want to delete stop words. So I'm going to go ahead and keep our stop words. Why don't I just comment this out and then put a new one in where I'm not deleting the stop words, just so for all of your sake, you still have access to that one and you don't need to change any code. So I'm just going to delete this part of that Boolean statement. So I have filtered words. What I could do is print, if I'm curious, I want the unique words. This is a set of the filtered words, because remember, a set will only contain unique items, and we already have filtered words, right? And so the lexical diversity of this text is simply, and this is sometimes also referred to as the type token ratio. A type is a unique token. A token is just the actual items themselves. And so here, all I want to do is I want to divide them. So I want to divide the length of our unique words by the length of filtered words. And so we'll print this just for fun. Print lexical diversity, and we'll go ahead and run this. I'm gonna not print the most common here. Clear and run. And so now we'll see, this is kind of a quick and dirty measure of a text's vocabulary. And so 7% of the words in this particular text are unique. And so that's kind of cool to know. There is actually a really good demonstration of this online where somebody mapped out the lexical diversity of a bunch of rap artists, and it's really quite fascinating. And because rap as a genre tends to have a very high lexical diversity because it's very lyrics focused. But you can see people at different ends of the distribution. So DMX is very low on the distribution, whereas the Wu-Tang Clan is really, really high. And so when I teach this, I always like to, play these songs for my students and kind of show like how lexical diversity kind of impacts the experience of listening to something or reading something. And I always make sure to say that lexical diversity is not a measure of how good something is, because there are songs that are highly repetitious that are just as good or better than songs that have almost no repeated words in them. Because kind of what builds a good rap song isn't just the lyrics, but it's also things like rhythm and flow and musicality, and that's just something to keep in mind. So you don't want to kind of read this as a normative judgment, okay? Anyway, that's sometimes something, this is a useful metric for doing authorship detection, if that is something you're interested in doing. So, okay, so I've kind of gone a little bit on a tangent here, but just so you know that is something you can do. You now have the code to do that. I will keep that in here. But let's continue to refine this process. So what we might want to do is we might want to stem our words. So the process of stemming is removing conjugation, right? So this is not something we need to do in Chinese because words are not inflected. It is definitely something you want to do in English in a lot of cases. You might want to do it in a language like Finnish, although if you work in Finnish, that's tough. That is one of the hardest languages, or Hungarian, I think, are the two most difficult languages that are relatively widely used for people who are interested in natural language processing, just because their grammar is so complex. So that's kind of not really the point right now, though. Let's stem this text. So if you are working with the Natural Language Toolkit, what you need to do is you need to import your stemmer object. So you can say from nltk.stem.snowball, import snowball stemmer. Now this snowball stemmer, I do believe, has a number of different languages built into it by default, so you will have to pick the one that you want to use. But that's simple enough. The first thing we need to do is we need to create a stemmer object. And basically that's just the thing that's going to do our stemming for us. And so I'll need this before I try to do this. So I'm just going to make it somewhere at the top of my text, and I might do it, say, here on line 10. I'm just going to say stemmer equals snowball stemmer, and then inside parentheses I need to give it languages. And actually, I'm not sure if you can see this help. Yes, you can. That's great. There's Arabic, Danish, Dutch, English. Hey, it has Finnish and Hungarian, Italian, Norwegian, Portuguese, Romanian, Russian, Spanish, and Swedish. So actually that's pretty good. So this will basically cut off the conjugations of our words. And I'll show you what that looks like here in a moment. So I'm going to be using English because we are looking at this Sherlock Holmes text. And like I mentioned before, I want to do this in some place where I'm not going to have to iterate across my text more than once. And so that means I want to do it here on line 28 in the process of creating this filtered word list. Fortunately, we can adjust this word variable here with any function or method that we want. So the way we would stem an individual word is we would simply say stemmer.stem running, right? So this will hopefully cut off the ning and just leave run. Okay? So I want to do this, and I'm going to do this for every word in this document. So I'm going to say stemmer.stem word. Now, this will add a little bit to the processing time of my text, but if I rerun this code, we should see that our top 10 words have changed a little bit. And let's go ahead and take a look at what that looks like. Whoops, I'm not printing most common. But you can see here that the number of unique terms has gone down. You can actually see that there was a 2% decrease in the number of unique terms just by removing conjugation. So that is something to be aware of as just kind of a property of language, I guess, or as a property of an author. So I'll run this, and that let's see why. Oh, I failed to save it. That's my fault. Okay. I mean, it's always my fault. But okay, now we can see, okay, we're back at the, I, and, to, of. So let's go ahead and filter it without stop words. And word not in my stop words. Okay. Let's go ahead and run this. Said upon home one would man could little see come. Okay, so now you can see it has cut off the conjugation, but there's a problem. Homes should not have been stemmed, right? It is grammatically a noun. It is not conjugated. So what's going on? Well, the process of stemming does not check to see if the word that it produces is a real word. if we want to make sure that the word that actually emerges is a real word, we need to do a slightly different process known as lemmatization. The reason we might not always want to lemmatize is that it is a significantly more computationally expensive process. And by that, all I mean is it takes a lot longer to run. And so we don't often, or we don't always want to do that. Stemming is, in fact, much, much quicker. So I'll show you how to lemmatize, and fortunately, it's pretty simple, for English anyway. I'm going to show you how to lemmatize with a different package in a moment when we build a pipeline for a little bit of analysis. We're going to get to that here in a minute. But first, let me show you how you would lemmatize with the Natural Language Toolkit. So I'm going to go back up here to the top, and actually I don't need to import anything for this because it actually comes with NLTK right out of the box. Instead of this stemmer object, what I want to do is I am going to call this a lemmatizer equals NLTK.wordNetLemmatizer. And WordNet is a corpus that a lot of people use to train these sorts of models. And so now, all I need to do, instead of down here calling stemmer.stem, I'm going to call lemmatizer.lemmatize. Okay? And that's the only difference. Now, instead of getting those stems, we're going to get the lemmas. And we'll take a look at what that looks like instead. Now, this will take a little bit longer to run. Let me check. Yeah, I saved it. Excuse me. So this will take a little bit longer to run, but it's not so bad in this context. So now you can see said, upon, Holmes, won, would, man, could, little, see, may. You can see now that this works fairly well. So now we can actually see how often certain words are used without having to worry about whether or not they are conjugated in a certain way. Now, this does mean that if we want to build a search functionality for this, we need to be lemmatizing the search term as well. So, for example, if I wanted to look through this list and count up how often the word murder, for example, appears in Sherlock Holmes, I would need to lemmatize it if I searched for something like murders. Okay? So just keep that in mind, and I'll try to remember to account for that when we build our little script here in a few minutes. So that is what I wanted to say about the Natural Language Toolkit, but I want to kind of step back and talk a little bit about doing these same sort of analyses in languages that aren't English, and particularly in languages like Chinese. And I realize that many of the viewers out there probably don't read Chinese, but this is my own area of expertise and interest. And so I'm going to spend a little bit of time discussing it and show you some of the tools that are out there that will allow you to do this. Because I'm going to start a new script here, and I'm just going to call it I'll just say other lang processing .py. My demo sentence, and this is some sentence in Chinese, right? And so it could be something like 我的名字叫李有人. Okay, which why does it do that? 人. Okay, so let's imagine that I have a sentence that looks like this. Now, you can see that it might actually be kind of complicated to break this apart into individual words. Okay? So if I did something like print demo sentence split using spaces like with English, if I run Python, I saw that this, what is it? Demo sentence. We can actually see that it just gives me a list with one item in it. That obviously is not a word. And so I can't depend on one of these sort of really basic heuristic methods for dividing this into words. One option, and this is often an option that those who work with very classical texts turn to, is simply dividing it into characters. So if I just run .split, I think it might still try to do by space, yeah. So I could say list demo sentence to get the individual characters. Let's get rid of that period. Okay, so if I run this, you can see that it divides it into individual characters. But again, in modern Chinese, this isn't super useful because 我 just means I. De is a particle that turns I into my, right? It's a possessive particle. Ming is a name, 字 is character, 名字 in modern Chinese is just name. 叫 is a verb that's just to be called. So my name is, and then my name is, Li You Ren, right? So it's Li You Ren. But it doesn't make sense to think of this as an individual, is each character as having kind of the same semantic level, because they don't. So we're going to need to do something a little bit more sophisticated, and we're going to have to turn to specific libraries. And probably the most popular library for Chinese is Jieba. And so the thing you need to know, however, is that this is it does not come with Anaconda. So if you want it, if you work with Chinese texts, particularly modern Chinese texts, is there any way for the prompt window to read Chinese characters? Yes, there is, but you have to change the default font in the prompt. So if you go into properties, you'll have to change it to a font that actually displays Chinese. Because unfortunately, by default, it doesn't, which is, in 2020 or 2021, is wild. It really should display it. But yeah, you have to change the font to something. I think Simsun is one of the common fonts in Windows for this. And yeah, so that would be how you would do that. Macs are nice because they will display any UTF-8 character that it knows of. So if I don't have Jieba installed already, from my terminal, I want to run pip install with 2 L's Jieba. And when I hit enter, it'll run it, right? And it actually is just telling me, hey, you already have this installed. So this is probably the most commonly used modern Chinese segmenter. There are lots of others out there. There are some made by Stanford. There are some made by the academia team called the CKIP lab at the Academia Sinica. There is a segmenter that is made by people at Beijing University called PKU Seg. So there are a lot of options out there. I'm going to show you how to use Jieba though. But you're going to have to install it. But I will put this link here for their documentation. And so if you go to github.com/fxsy/Jieba, you can find it. This will go on, well, actually, why don't I put this into the chat? And I would show you their website, but unfortunately, I'm not set up to capture Chrome. Anyway, because I'm on my laptop. So let's go ahead and use this. So I'm going to import Jieba, and then what I'm going to do is I am going to simply call jieba.cut demo sentence. And I'll just say words equal this. Excuse me. And so I'm going to print words. And so when I run Python, other language processing, okay, actually, we can see that this is a generator object. That means it's going to give us something that will act as an iterator. It'll basically go through and pump out individual words. So one easy way to deal with this is we can just put it inside, we can turn it into a list instead of a generator, right? And so now, when I run this, we can see that it breaks up 我的名字叫李友仁. So you can actually see that this breaks up I and possessive into individual words, which is fine. Maybe philosophically, we could say it should be my, like 我的 should be a word. But, this is pretty good and way better than what we had before. And in fact, this probably matches up with most English tokenizers, where if you had, somebody's car, somebody, it would be one word, S would be another word, and car would be another word. So maybe it's not so strange here. Okay? So that's one way of dealing with Chinese. That is for modern Chinese, however. Let's say, what happens though if you're working with a text that is written in classical Chinese? And as I've mentioned before, this is where things get a little bit more difficult and complex. There are a lot of reasons why there's not a great classical tokenizer out there. One of them is the sheer diversity of the language that is written in classical Chinese. So a Ming Dynasty or a Yuan Dynasty novel is going to be written with completely different language than, let's say, a Song Dynasty philosophical text. So, for example, if you're reading something by Zhu Xi, who was a 11th century Neo-Confucian philosopher, the way that he is writing is just, it looks nothing like, say, a play by Guan Hanqing, right? They just don't, it's hard to call them actually the same language. And so this makes it extremely difficult to build a model that will tokenize all of the things that we think of as classical Chinese. The other thing is there's simply not a lot of money in it. Google's probably not super enthusiastic of developing a tokenizer for, 2nd century BC philosophical texts, because not particularly monetizable. For modern Chinese, we want machine translation, we want text-to-speech, we want all of these sorts of things. Not a lot of market for this for classical. That being said, there is at least one classical model that is available for everybody to use via the Stanza project. There are also models out there that aren't publicly available yet. So the CBeta group which is they essentially have an amazing corpus of Buddhist texts. They have a Buddhist tokenizer. The CKIP group, I think, has a tokenizer. I know of people at Tsinghua University who are working on it. So there are options, right? But one of the ones that we have available to us as just folks out there is the Stanza classifier. And this was trained by a group of scholars at Kyoto University. But we're going to need a different library for this. And so in this case, we're going to need to install Stanza. So Stanza is a multilingual NLP suite that is put out by the Stanford Natural Language Processing Group. And it has a lot of very, very good models to study lots and lots of different languages. And I already have this installed, so it's going to run through and it's going to say, hey, you already have this installed. But if you don't, I'll put this in the chat. You can run pip install Stanza to install this. And I'll also put the link to the available models in the chat. So these different models, it really has, actually, let me take a look here. So Stanza, available models, let's see. It has Afrikaans, Ancient Greek, Arabic, Armenian, Basque, Belarusian, Bulgarian, Buryat, Catalan, Simplified Chinese, Traditional Chinese, Classical Chinese, Coptic, Croatian, Czech, Danish, Dutch, English, Estonian, and so on and so forth. Many, many different languages. And for those of you who work in historical documents, there is even a model for Old Church Slavonic, or Old French, or Old Russian, Old English. There's actually not one for Old English. But regardless, there's a lot of stuff out there. Go check it out. It's really, really an amazing project. So let's take a look at this. So you do need to download the models that come with Stanza in order to actually use them. So I'm going to make sure, yeah, you can still see my screen here, so we're good. I'm going to clear this off. And let's go back to the code here. So I'm going to, at the top of my code, import Stanza. And so this will let me use the Stanza library. But I need to download and install my model. So I'm going to install the model. This only needs to be run once. Only needs to run once. This is like the NLTK.download that we talked about last time. But this, if you already have it downloaded, it will actually just download an update in case you don't have the most recent version. Excuse me. So you can say stanza.download, and then inside these parentheses, you will give it the model that you want. And if you go to that available models link, and I do want to put this here as well, and from there you can get the codes for the various models. So LZH is a classical Chinese model. So this will be classical Chinese. It needs to be spelled correctly, Stanza. But I can also install traditional Chinese, which is ZH Han Ti. And then there is a simplified, which is just ZH. So this is simplified, and this is traditional. So once you have downloaded these models, you can actually use the Stanza pipeline to do natural language processing. And I'll show you how that works. So the way that you do this is you create a pipeline. And so the way they recommend it is you do something like NLP equals stanza.pipeline, and you give it the model you're going to use. In this case, I'm going to use classical Chinese. And then I'm going to give it processors, and this is optional. And this tells it what are the different ways we're going to process this. In this particular case, I want to tokenize it, and I want to have parts of speech, POS. Okay? And so this is a little bit weird in that the way they want it is a string that's separated by commas, but you know, it is what it is. And so this will create an NLP object that I can use to perform analysis. So what I'm going to do here, instead of, well, let me just comment these out instead. So now I'm going to say doc equals NLP demo sentence. And so this model thinks that the input that I'm giving it is classical Chinese. And to get information out of it, this will create a document object that has sentences, and for each sentence there are words, and in those words we have information. So I can iterate through this to say for sentence in doc.sentences, for word in sentence.words, I'm just going to print word.text and word.part of speech. Okay? So when I run this, it will tell me what this classical model thinks the parts of speech of these different terms are. Now, it's going to be completely wrong because this is not classical Chinese, but we can run it, right? So I'm going to run Python other language processing. Line 6. This needs to be commented out, of course. And let's try that again. And so it's going to download the models, and then it'll have those on hand for us to actually run our analysis. And we're going to kind of see how well my internet handles this because I'm streaming at the same time, and it might get jammed up. But also, please feel free to put any questions you might have in the chat window. And I might stop this if it takes too long. And in fact, I think I will I'm going to comment out these downloads because I've actually already downloaded these on this computer. And it generally doesn't take this long, so I'm not precisely sure what the issue is. But I'm going to rerun this code without downloading these because I do have them on my disk. You will need to do this beforehand anyway. I failed to save it. So I'm going to try again. Okay. This time it should be just fine. Not enough. Let's see here. What have I done incorrectly? Let's see. So for key split. So sometimes you're going to run into errors like this, and when the errors happen in other, in somebody else's code, they can be a little bit harder to deal with. But I'm just going to get rid of this option here and see if that clears it up for us, because sometimes that does. That fixed it. Okay. So what's happening here? Well, this model, which is a machine learning model, is going to try to identify how these words divide up, and then it's going to use its knowledge of classical Chinese to try to guess what the part of speech that is. And it's also going to look at the context of the sentence. So if we look at this, we can see that the part of speech here is, if you could not find a version that satisfies the requirement torch. So there is a dependency of Stanza that is PyTorch. And PyTorch may or may not be installed on your computer. If this remains an issue, I would say we'll try SpaCy here in a minute, and hopefully you won't run into that issue. But yeah, it's because whatever version of PyTorch you have installed is not compatible. So that's a little bit unusual, but it does happen. And either you can reinstall PyTorch. Usually it should handle it itself, but sometimes it's just kind of weird. But hopefully Stanza will work even if this doesn't. So we can see this is correct. I is a pronoun, but de is not a noun. Mingzi is technically a noun. So that's correct, but zi is definitely not a verb. Jiao is a verb. Li is a noun. But you can see that if you try to parse it in classical, it just doesn't work. So just unfortunately, that is the issue. So I could instead use the ZH pipeline and hope that this runs a little bit better. And we can just run it to see. In this particular case, it takes a moment to load. And we can actually see the different things it can do. It can do sentiment analysis. It can do lemmatization. And this is actually a lot better. So pronoun, a particle, a noun. Well, it messed up here on my name. So it's better. When you print parts of speech, can you print verbs only? Absolutely. In order to do that, all I would need to do is I would need to say if word.pos equals verb, and then tab that out. And then if we run this, it will only print the words that it thinks are verbs. And you can see this isn't great necessarily for Chinese as it is, but it's not awful either. And so it'll take a second to kind of load this back in. Stanza is very resource intensive, and so often it's going to be a little bit, slower than other options. But you can see here that it picked up on the thing that it thought was a verb here. All right? Okay, so the last thing I want to talk about is SpaCy. SpaCy is a relative newcomer to the scene. I think it's only been around for maybe, actually I shouldn't say, because I don't know how long it's been around. SpaCy is an excellent option for multilingual natural language processing. And there are a lot of really, really good tutorials out there on how to use it, on how to kind of build interesting tools that depend on it. And I'm going to show you briefly how to go about doing this. So to install it, you'll also need to run pip install SpaCy, which I have put in the chat. And I will also put on here a link to their documentation so you can kind of see how you go about actually using this. So in a minute, I'm going to take a couple-minute break, but I'm going to go ahead and run to like 3:15 or 3:20 because I did get a late start. So we're going to spend the last half of this building something together. But I do want to get through this SpaCy part really quickly. So from the command line, you will simply run pip install SpaCy if you don't have it installed. I do, and it will run, and my hope is that this doesn't depend on PyTorch, but it might. I don't see it here, but good luck. Now, like Stanza, for SpaCy, we do need to download the models we want to use. Now, SpaCy comes with, again, a really wide variety of models. If you go to their website, it will tell you a lot about all of them. I'm going to clear. Oops, that's the wrong place. Let's see here. Okay. Oh, great. That one works. I'm glad to hear that. So I lost place in my notes here. Okay, here we go. The first thing we want to do is after you've installed SpaCy, you might want to download the model you're going to use for your processing. You might, for example, want to use Chinese, and in this case, this is a modern Chinese model. And the code is going to look like this. I'm going to post it here in the chat, so you can copy that if you want. That is for Chinese, which I've already downloaded, so hopefully it'll just say, hey, this is already satisfied. It looks like it. So the way that you do this is python-m SpaCy download, and then the name of the model you want. So if you want an English model, let me grab my notes here. This is the English model, which I'll put in chat. And there are also bigger models that are often, they perform better, but they take up more disk space, and so on and so forth. And then here is a French model, right? And we're going to use that for our French pipeline that we're going to build here in a second. It's going to be a multilingual pipeline. So let's just go ahead and comment these out. And here I'm going to import SpaCy. Now, SpaCy is a great library, like I said, because it has a lot of really good tools. The syntax is pretty similar to Stanza, in fact, but let me pull up my notes. You really get used to multiple monitors, and as soon as you don't have them, life just gets way more complex. Okay, I think I'm back here. Okay, so to use it, we have imported SpaCy, and we're going to say something like NLP equals SpaCy.load, and then the name of the model that we want to use for our language. So for Chinese, it would be ZH Core Web SM. That's a small model. For French, it's just, what is it? It's FR Core News. Oops. News SM, and then for English, it is EN Core Web SM. Now, of course, if I actually ran this code, the only NLP object that would remain in memory by the time I get to line 31 is going to be this one right here, this last one. So I could say something like Chinese NLP, French NLP, and English NLP. If I wanted to have all of these in memory, but really the fact is most of the time you're not going to be trying to parse both a French and a Chinese document in the same script. So, you can just leave it as is, only load in what you actually want to use. We can also say doc equals NLP demo sentence, right? So here I'm going to try to use this, I'll uncomment my demo sentence, and I'll say demo sentence here. and I'm just going to make sure that my NLP object is the Chinese one. And so now I can access this document object to get my lemmatized information, or not my lemmatized information, but my tokenized information. Now SpaCy is a little bit different. So SpaCy's model is only in a single layer. That is, there is no sentences object to deal with when we deal with this. So I can simply say something like words equal word.text for word in doc. Okay? And if I print words, we can see how SpaCy handles this. And I can tell you how SpaCy is going to handle it immediately. It actually just uses Jieba to tokenize. So that that is just how it is. So Python other language processing.py, and it'll take a second to think about what it's trying to do, and then it should run. Now this is a long time to process a single sentence, but here you can see that it has successfully identified my name here, which is awesome. So there we have a super quick introduction to SpaCy, but we're gonna dive a little bit deeper into it. Well, actually, why don't I really quickly show you one last thing, and then I'm gonna refill my water, and then we can come back. So here what we'll do is we'll say, I'll just give it an English sent, and this is going to equal hello, my name is Paul. Okay? And so if I said ing doc equals NLP English sent, then what I can do is I can say in English words equals word.lemma underscore for word in doc, and that should be in doc, and this will give me the lemmas. So it actually lemmatizes by default, which is a pretty handy thing to know about. So I'm going to print in words, and then we can see that well, unfortunately that sentence might only be lemmas as it is anyway. Right, my name is Paul. Yeah, well, we'll see if it changes is to be. I'm not sure that it would actually do that. It might just say is. Yeah, it just says is, but and he runs. Hello, his name is Paul and he runs. So runs should just end up being run if this works properly. And so you can kind of see that this is a little bit more expensive than the NLTK models that we were using, but that is often the price we'll pay for really good processing. No, it looks like it processed it as runs. I am not precisely sure why that's the case, but this should be the way that you grab lemma out of a model. So we may have to come back to that. But I want to grab a little bit more water, and I will rejoin you here in a sec. Because I'm on my laptop, I don't have my little screen that I can cut away to. I'm just going to kill my mic for a second, and I will be All right, I remember to turn the mic back on so I'm not here. The message, can't find model English Core Web SM. If that's the case, make sure that you ran the installation. So you'll need to run first python-m SpaCy download this right here. If you haven't done that, then you won't be able to use the model. Hopefully that'll be the issue, but hard to say. Okay, so let me make sure I am organized here, and then we're gonna finish this off hopefully with something a little bit. We're gonna put all of this together and we're gonna build a little visualizer, okay? And this will get a little bit complex, but I'm gonna do my best to not let it get out of hand, okay? This is sometimes I'm not great at that, but we'll see how this goes along. Let me pull up my notes here. And I put together a little multilingual processing pipeline this morning, and I tested it, but you never know if these things will actually work when you try to do it in front of people. We're gonna give it the old college try, right? Okay, so I'm gonna start a new script that I'm gonna just call analysis pipeline, something like that, analysis pipeline.py, and I will save it inside from 0 to n. Okay, so let's go ahead and do this. So essentially what I want to do is I want to be able to give my script a word, and then I'm going to want that script to visualize where that word appears across documents within my corpus. So remember, I have these three corpora. I have the English one, I have the Chinese one, and the French one. So what is going to be the process for doing this? Well, first I'm going to import the various libraries that I'm going to need. So we'll just call this a pipeline to visualize word frequencies. And there will be lots of places that you can improve this. For example, you can think about, well, if I'm always analyzing the same collection of texts, maybe I want to save the state of the corpus after it's been cleaned up or after it's been tokenized. And you can also think about improving it in other ways, speeding it up, visualizing multiple words, for example. There are going to be a lot of options, but first we're going to need a few of the libraries that we've already talked about. So I'm going to import Stanza, SpaCy, the regular expression library, and OS. Now, this regular expression library, I'm not going to get too into regular expressions because, again, lack of time, but I am going to use a couple of kind of basic ones to split these texts apart into individual chunks. But there may be better ways of doing that also. And also, I'm going to import matplotlib.pyplot as PLT. And I mentioned this yesterday when I was talking about libraries, right? So we're going to use matplotlib as PLT. So now what I want to do is I want to break apart my code into functions that are reusable and will let me kind of scaffold what I'm doing. So the first thing I want to do is I actually want to load the model that I'm going to use to do the processing. Okay, so if I'm only ever going to be loading a single language, this isn't really necessary, but because I think for demonstration purposes it's kind of nice to build it in a way where we can just use the same script to do all of the corpora, that's what I'm going to do. So I'm going to define something that I'm going to call load model, and I want to give it a language, right? So I want to give it English, French, Chinese, or classical Chinese. Okay, these are the different languages that I want this script to be able to handle. And so what I can do is, and this is not, of course, the most efficient way of doing it, but we're going to make it pretty explicit. So I'm going to check if the language, that's not how you spell language, language, if it's English, I want to use SpaCy.load in core web SM. If language is French, I'm going to use NLP.spacy.load NLP equals, spacy.load, and I will give it fr underscore core news sm, and also equals Chinese, NLP equals spacy.load zh core web sm. And unfortunately, SpaCy does not, to my knowledge, have a classical language parser, although if it does and you know about it, please do tell me. I'm going to, didn't want to do that. I'm going to say elif language equals classical Chinese, NLP equals stanza dot pipeline, and then I'll give it LZH. Okay? Now, this might not be completely best practice because here we have an NLP object that is going to function a little bit differently if it's classical Chinese as compared to the other models. But you know, it's convenient, so I'm going to return NLP, and then we are going to move along. Okay, so now we have a little function that in order to load a model, I can just say something like NLP equals load model English. And so that's a lot handier than having to say equals spacy.load in core web sm, right? And so I could extend this by having different, more different languages that I'm loading in. I could also use a dictionary. You know, for example, I could say something like model dict equals this, and I could have English point to spacy.load. I don't really like doing that, and I also don't think Python's too keen on you performing kind of actions in dictionary creation. But anyway, this is how I'm doing it, and that is just how it's going to go. Okay, so let's think about how we might want to process an individual text that we're reading in, and this could be kind of arbitrarily English, Chinese, or French. So I'm going to get rid of that. And I want to write a function where I'm going to process my text. And so here I'm going to give it a variable that I'm calling text. Again, this could be whatever I want to call it. I'm going to give it a language, and I'm going to give it the NLP object that we're going to need to do the processing. So I want all of my text cleaning and processing to happen inside this document. And so here's where I'm going to handle it differently depending on the language that it is. Well, first I want to get my document, and I'm going to get it NLP text. But if I want everything lowercase, I can go ahead and make it lowercase right here. Right? I want this processing to happen inside this function, so I'm going to do that. And then I'm going to have an easy if-else statement to deal with the language. So here I'm going to say if language is classical Chinese, what I want is a list of those words. So I'm going to say words equal word.text for sentence in doc.sentences for word in sentences.words. And so I'll walk through what's going on here. So this is a list comprehension that is very similar to the ones we have been talking about, only instead of one loop, I actually have two loops in here. And so the way that this syntax works is I have my outer loop here, which is for sentence in doc.sentences, and we've seen this syntax in this workshop. And then I have my inner loop, which takes this sentence variable, and then I say for word in sentence dot words, get the word dot text. And so this is what gets saved to our list. This is the outer loop, and this is the inner loop. Okay, and this will provide me with a list of words that has just the text in them. Because remember, I don't need to lemmatize anything if it's in Chinese. If it's in modern Chinese, I want to use a SpaCy model. So I'm going to say if language equals of course, equal Chinese, what I'm going to say is words equal word.text for word in doc. And the reason the syntax is different here is because the NLP object that I have is different if the language is Chinese versus if it is not Chinese, or if it's classical Chinese, because I'm using SpaCy down here and Stanza up here. Again, less than ideal, but we work with the tools we have access to. Otherwise, if it's not Chinese, I want the lemmas. So I'm going to say words equal word.lemma for word in doc if word.lemma underscore dot is alno. So here I'm adding an extra filtering process where I'm basically saying, hey, let's make sure that this word is alphanumeric. And we could add that up here as well, but I'm not really going to worry about it because in many cases classical Chinese doesn't have punctuation anyway. In this case it actually does. So here I'll add this if word dot text dot is alno. We'll just add that up here. If word dot text dot is alno. Okay? And so this word dot text syntax here is basically taking a SpaCy word object and just getting the string out of it. Okay? And then I want, here I want to return words. So this is my process text function. And so it takes just a long string in. I tell it what language it is, and I also give it the NLP model that I want to use that I've loaded with load model. Okay? There is one further step that I might want to take in this process of cleaning up the text, and that is to adjust the spaces in it. So you might remember from last time when we were working with these Project Gutenberg texts that new line characters get really jumbled. Well, I might want to actually take any time a new line character occurs inside of a paragraph, I want to replace that with a space. And I can do that with regular expressions. And here, you'll have to take my word for it, but you can see one demonstrated case of using a regular expression. I'm going to create a new function, and I'm going to call it clean spaces text. And here I'm just going to replace single new lines with space. And here I'll just return. I'm going to use the regular expression library. I'm going to use its substitute method. And then what I give is a pattern to match, the thing to replace it with, in this case a space, and then the string that we're going to change, in this case text. So what is the pattern I want to match? Well, you remember that \n represents a new line character, but I don't want to replace all new line characters with spaces because sometimes they divide paragraphs. But note, in Project Gutenberg texts, there's more than one new line character. In every case, you have a new paragraph. You usually have 2 or 3. So I can say match new line characters, but look ahead to the next character and ask, is that a new line character? And so to do that, I use what is known as a negative look ahead. And again, I apologize, we haven't talked about regular expressions. All this does is it simply says, oh, I found a new line. what's the next character? If the next character is not a new line, then go ahead and replace that new line with a space. And so this will get rid of all of those internal new lines that I don't care about. Okay? And that is that. So now let's write a function that kind of loads in every text in our file, or every text in our directory, and does something with it. Okay? And it runs this process. This is kind of our, it's not necessarily our full main function, but it's going to be a big part of it. I'm going to define another function that I'm going to call load corpus. I'm going to give it the directory. I'm going to give it the language. And I could give it a regular expression to divide these texts internally, but I think actually I'm going to keep it simple and not do that. And maybe I'll leave it up to you to figure out how to do that, or maybe I'll upload a supplementary thing that also shows it. We'll see how people are feeling, because what this will do is this will treat every file in a language, or every file in a folder, as an individual instance that we want to analyze. So I want a couple of variables to keep track of information for me. I want a list for my processed texts, and I want a list for my labels. Now, of course, I could use a dictionary here instead, but this is how I'm going to do this. Now I need an NLP model, right? I need NLP, and this is going to equal load model. And here, if you notice up here, I have defined load model, so I can just feed in the language. So when somebody runs this load corpus method, or this load corpus function, they'll specify the language, and that will get passed to the load model function. And so this will create an NLP object that I am going to use to tokenize my documents. So you're going to see here that we're kind of adding all of the different parts that we've covered in this workshop together to make this script, right? Now, of course, like I said before, in many cases, you're not going to have a multilingual script like this, but, you know, it's good practice, okay? So the next thing I want to do is I want to iterate through every file in my folder. I want to open it, clean it, tokenize it, and then save it, okay? So here, I'm going to say for root, there's files in os.walk directory. So remember, we talked about this previously. This is how we iterate through every item in a folder. Then here, I'll simply say for fname in files. And here, I'll go ahead and make sure we're not pulling up any hidden files. So I'll say if fname 0 is not a period, then we want to continue. And we want to say with open os.path.join root fname. We're going to be reading this, and our encoding is UTF-8 as our F. So this is all from last time when we talked about opening multiple files, right? So, but now we're kind of adding all of these things together. So we're going to go through every file name in files. We'll check if it starts with a period. If it doesn't start with a period, we're going to continue, and we'll open it using this context manager. So I'm going to say text equals rf.read, and then I'm going to clean the spaces. Now, actually, thinking about this now that I'm looking at it again, if you remember, our process text function is where we want to do all of our text processing. In this particular case, we might want to do something like text equals text.lower, and then we'll say text equals clean spaces text, and then we'll just give it text by itself, right? So this way, all of the text processing happens inside of this function right here. And that way, I don't need to remember to do anything with the text outside of this function. Now, this should run but I'm going to move clean spaces to before process text just because I kind of like to have my functions defined before I run them, right? So now what we do is we have text, and what I want to do at this point is I want to go ahead and say, let's see, how do I want to do this? I'm going to say words equal process text, and I'm going to give it text, I'm going to give it language, and I'm going to give it NLP, right? Because remember, what's going to happen is I am going to feed a string into this process text function. I'm going to give it the language, and I'm going to give it this NLP object. Inside process text, it makes it lowercase, and we can run this on Chinese. It's just not going to do anything, so it's not really an issue. We're going to clean up the spaces. We're going to create a doc object. Then we're going to create a words list, but it's going to vary depending on the language, if it's classical Chinese, Chinese, or something else. Okay? And then we're going to return a words list. Now we'll say words equals process text. And then I want to also say labels, and we're going to append our file name without .txt. Append, let's just do f string, and then we'll do f name -4. And so this will just append into this labels list a label that we're actually going to be using to do our visualization. And finally, I want to say text.append, texts, that's difficult to say, dot append words. So, and then finally return texts and labels. So in your return from your functions, you can actually return multiple different items. You can, and it'll come back to you technically as a tuple, and where the list of words comes first and the list of labels comes next. So we're almost there. We are almost to where we can run this code. But I'm going to define one very last function before we move on. And to do that, this is going to be our visualization function. I'm going to say def viz term, and I'm going to give it my term. This is what word am I going to search for. Excuse me. I'm going to give it texts, and I'm going to give it labels. What I want to actually visualize is how often does a term appear in a document. So here I'm going to say term counts is going to equal text.count term for text in texts. So keep in mind that this texts list is going to contain a list of all of the words in a document. And so I'm just counting how often whatever term I'm interested in appears in this document, right? And I also, in fact, might want to adjust for the length of the text, because it's not particularly meaningful if the word Holmes appears 30 times in one short story and 20 times in another if the first one is 30% longer, right? So we might want to adjust for that. And we can do that simply by dividing by the length of text, okay? Or if we wanted to be very clear, we could say for words, right? And this is the advantage of this is that, you know, it's clear that the words here are in fact the words that are appearing up here as well. But again, that doesn't matter a whole lot. So here's where we're going to create our plot. We're going to say plt, which is our pyplot module. I want to make sure that my x ticks are rotated by 90 degrees, because the more bars I have, the more it's going to be hard to read it if they're not rotated. Okay? Then I am going to say plot.bar. I'll give it the list of labels, and I'll give it my term counts. Then finally, because you always need to show, I'm going to do plt.show. Now, I will warn you that when you run plt.show, it will open up a window, and that window is technically running in a while loop. And your computer, when it draws things, is running in while loops. And if you don't close that window, it'll seem like your script is just running forever. And it can be kind of frustrating because it's very easy to forget to close it if you're kind of adjusting things here and there and kind of tinkering with all of it. So that's basically it. We now have our script. Now, if we're being good programmers, we will add a little piece of code at the end that says, hey, I only want to execute the following code if I am running this directly rather than importing it. So if you've ever seen something called if underscore underscore name underscore stunt underscore equals, and in quotation marks underscore main underscore underscore, all this is saying is for the following code, anything after line 56, if I want it to execute, I have to type Python space analysis pipeline from my terminal. If I import it elsewhere, this will not run. Okay, so this is kind of just good practice to do, and because now we have a real script that does something, it's a good idea for us to do it here. So let's do this. The first thing I want to do is I want to get my texts and my labels. This is equals load corpus. And let's, for the moment, start with English. And in this case, that's all I need to tell it because the language is by default English. Then I'm going to say viz term, and then the term I'm going to visualize is, I don't know, let's say homes. It's not very interesting, but you know, let's go ahead and do it. And I'm going to say texts and labels. Okay? So, assuming I have done nothing wrong, this will run and it will it'll make a bar chart in the 3 texts that I have of the Sherlock Holmes short stories of how often Holmes appears. So I'll clear this and I'll run this, and it will admittedly be a miracle if this actually works first shot, but we're going to go ahead and we're going to run it. And it kind of seems like it's running, but do note that SpaCy the processing time is not immediate. And so we're going to add, I think, one more thing that's going to let us see what's going on. We're going to add a print statement to make sure this isn't getting hung up somewhere in the process of actually running our code. Because as you can see right now, my computer is thinking. And it's actually partially thinking so hard because I'm using a lot of my processing power to stream right now. And this isn't also a super powerful computer. It is a few years old. And so that does make a difference in how long it takes to actually process something. If you're on a desktop computer, this should actually run pretty quickly. But what I will do is I'm going to add a print statement inside my code that kind of prints and tells me what's happening in this process. So for example, I might in my load corpus file actually, shout out, hey, this is what's going on. So I might say something like, trying to decide where is a good place to do this. It finished running, and I'm not sure if you're going to be able to see that. You're not. Let me add another capture here. What's going to be? I'm going to add a window capture, and I'll go ahead and say graph. Sorry, I'm playing around with OBS to make sure that you can see the output of this graph. Oh, goodness, I'm not even sure what it's going to be called. It's just Python here, so Python figure 1. I bet this is it. Oh, there it is. Okay, this is what it produced. So you can see that we have a graph here with the frequency of how often the word Holmes appears across these different texts. And so we're kind of actually getting close to a place where we're actually doing some interesting visualization here. But you can play around with this, this window, and it has, for example, what do you call this? A magnifying glass, so you can zoom in. And I think if you do Control and go the other direction, it's going to zoom out. You will note that it's hard to see the labels. That's something that is sometimes a little bit difficult to fix. But you can save this to disk, and it will let you save it as a PNG, most likely. And so you can keep these around. Now, it might be worth doing. I'm actually making a lot of work for myself here, because it might be worth streaming a little bit about the process of making visualizations that tell good stories, right? So how could I improve this? Well, I need a title, of course. I need labels for my axes. I need a legend that says what is the term I'm looking up here. And there are all sorts of ways that I could improve this. But for the moment, let's get rid of this here. We don't need that. Let's go back to the code really quick. And I want to print loading, and I'll make this an F string. And I'm going to go ahead and print fname. So here I can at least see what's happening as it processes through the text. And so I'll clear this off. If I run this again, we'll see that it's going to tell me, oh, hey, I'm loading Adventures of Sherlock Holmes.txt. And now at least I kind of have a sense of where in my script this is running. And this process takes a while because it has to find the lemmas and it has to do all of the tokenization. You could speed it up if you are doing lots of different searches on a document. You could actually save the lemmatized document and then load that in, so you don't need to do this again and again. But we could, of course, viz lots of different terms. So for example, here I could add another viz term, and I could say Watson, or I could say viz term crime, right? These are terms we would expect to appear throughout these texts. Now, excuse me, I would still need to give this texts and labels, texts and labels. And so the way that this will work is it will actually create the corpus only a single time, but it will create 3 individual plots for each of these different things. So an improvement, let's see, I'm not sure if I'm still capturing that. Yeah, it just ran again. But if I close this, it should finish running. And yeah, so let me close that as well. That always kind of throws me off my game as I'm doing that. So an improvement would be to put these on the same graph. It's already after 3, so we're definitely not going to have time for that today. But I can, of course, run this with the Chinese corpus, and I'm going to say this is modern Chinese because it's going to take a really long time to run. That classical Chinese model is extremely slow, and as I was testing this out this morning, it took like 10 minutes to run, which is kind of inexcusably slow as far as I'm concerned. So, there are ways of speeding it up, making sure it's only chunking really short sections of text. But we're going to see what happens when we do text, labels, load corpus, and let's visualize a few different terms from our Fengmenglong Sanyan corpus. So we might want to look for something like Zhongyi. Let's see. We might see how often does the term righteousness appear, right? So let's see. This is texts and labels. We might also want to look at something like which is humanity. We can see, do these terms appear throughout this? And I haven't tested this. I don't know for sure if any of these terms actually appear. I'll do viz term, and I know that, for example, the term ren actually does appear. So we'll just look at for ren by itself, and texts and labels. And so what we'll do now is we'll run this, and then I will show you how to divide this into smaller subdivisions, because I think that's actually going to make better looking graphs, because it's not super interesting when you only have 3 bars. So I'm going to run analysis pipeline, and we're about to find out if these terms actually appear in Feng Menglong's Sanyan. And so here we're loading the Jingshi Tongyan, and this is one of the 3 short story collections that Feng Menglong published in the 1620s. I don't remember the order he published them in, but each of them contain it's either 20 or 40 short stories, and I should remember this off the top of my head, but I don't, sadly. And each of these short stories, you know, there is kind of a mix of new stories that Feng himself wrote, some that earlier people had written and he's kind of editing to process anew, and it's just a fascinating collection, and there are very good English translations if you've never dealt with these. But it does take a while to run these, because we're talking about big books that need to be processed with a relatively slow algorithm. And so what I think I'm going to do here is I'm going to let this run in the background, and I'm going to show you how to subdivide these inside our script. So there are a few ways that we might approach this. One way of getting chunks from different texts to visualize independently would simply be to go in and put them in different files. And this is going to be the most reliable way, right? If you want to analyze the short stories written by Arthur Conan Doyle, you might want to divide them into individual texts and save them as individual files in your corpus folder. But sometimes you can you can always programmatically do that as well. And so I'm going to adjust this code slightly so it does that. Excuse me. So here what I'm going to do is I am going to, in my load corpus function, I'm going to add another parameter. And that parameter, I'm just going to call it divider. And it's going to look like this. And now what I'm going to do is I'm going to use this divider to split the text into sections. And this depends, admittedly, on regular expressions, which unfortunately we haven't talked about. But I'll show you how this goes. So instead of printing the file name right here, what I'm going to do is I'm going to take this text and I'm going to split it with a regular expression. So I'm going to say re.split, and I'm going to give it my divider, the text, and I'm going to make sure that this runs in a multi-line mode. And unfortunately, like I say, we don't really have time to discuss how this works, but I'll show it to you because I think it is a handy thing to see. So I'm going to call these sections, and now what I'm going to do is I am going to process each of these sections as an individual one. I'm going to get rid, in fact, of the first one because there's not going to be anything before the first divider. That's just kind of how these things work. And now what I'll do is I'll iterate through these sections and process them individually. So here I'm going to say for section in sections, and actually let's make this I, enumerate, which somebody had a question about before. We're going to enumerate these sections, and I'm going to tab this out so that happens inside this loop. And here I'm going to say print f processing section I of f name, just like this. And this way we're going to we'll see it'll look like it's running a little bit faster because we'll actually have independent things running that it's going to go up against. But let's say, okay, we're doing words, process text. And instead of text now, we want to give it section. And we want to make sure that we're including our number here. So we're going to append the section and the file that it comes from and return it. And so the only other thing we need to do is we need to give it a regular expression to use to divide the text. Now, the Sherlock Holmes short stories are divided by Roman numerals. So, and this is also true of Swan's Way, by the way, although there are only 2 Roman numerals in that. And I'm just going to say ing div is going to equal, this is going to equal a regular expression. It looks like the Jingshi Tongyan just finished. Let me make sure that you can see that really quickly. We have our graph here. Yeah, so we have, for example, different terms that show up in different texts. So in fact, some of them do show up, which is kind of cool news. I realize this is probably pretty difficult for you to see because it's just really hard for me to show this on this laptop. But I do want to do this very last thing here, and that is divide these texts up. So an English divider might be Roman numerals. Now, Roman numerals technically can't be fully validated in regular expressions, but if we give square brackets, this is saying, hey, pick any of these letters, I, V, or X, and I know none of them go above like 90, or they don't even get to 50, so I, V, X is enough. A plus is 1 or more times, and they're followed by a period. For Chinese, I want a regular expression that is something like a new line, and then maybe space, and then I'm going to give it D, which is like number, and then we're going to do a character set that is going to have Jieba and Bai, I guess, and maybe Ling. So sometimes they have 0 as well. I'm rushing because it is after, it's almost 3:15, and we want Jen here. Okay, so this will let us divide up. Each of the short stories is divided up by something that kind of looks like this. And so now all I need to do is I need to give it my divider. In this case, it is chindiv. And I think I'm just going to look up ren, just that single term. And we should be good to go. And so what will happen now is it'll go into these 3 collections of short stories, divide them into individual short stories, and see how often ren occurs in each of those stories. Assuming, again, that I have not messed this up. So I'm going to run this. I feel myself rushing, and I know that that's not good pedagogical practice. But here we are. Okay, so it's running. So we're processing section 0, 1, 2, 3, 4, 5, 6, 7. It'll do this for each short story in each of these collections, and it's going to tell us, it's going to give us a graph of how often ren occurs in all of these stories. And we now have a nice little viz of a single character. Okay? I'll let this run, and this will give us hopefully a nice looking graph. It'll at least give us a graph. But there are a lot of places where we could refine this. We could look at this regular expression and see, are there ways I can improve that? We could also divide our text internally into individual files by hand beforehand to make sure everything actually is an individual story. That's a perfectly valid thing to do. We could, for example, in our viz term, we could add a title here, and in fact we probably should, and that's going to be our term. And then at least we can see what is the term. The reason I kind of avoided this is that matplotlib does not play well with Chinese, sadly, and getting it to work on Macs is different than Windows. It's different on Linux. And I might put out a separate video on how to handle that. So let's see. Okay, so yeah, it's 40 short stories each. So now we're going through the second collection, the Xingshi Hengyan, and then we'll go through the last one, which I think is the Mingshi Yuyan, and we'll see what it looks like. But if anybody has any questions, please feel free to post them. I hope this is useful. I do know that this last session, we've introduced something much more complex, and we're starting to build things out in a way that can introduce issues when you're not really that experienced with these things. But my hope is that this kind of gives you the itch to learn more. You can look at, I again really will recommend Melanie Walsh's textbook. It's just really, really good. I have videos on my channel about doing many of these things. My last really comprehensive series was made 3 or 4 years ago already now, so it's a little bit out of date, but it's still useful. And I put up kind of continuing projects. I have not been as good about that since the pandemic started, but hopefully things will go fairly well. Is there a way to make a file in a right-to-left reading language iterate correctly? Yeah, so this should still work with Arabic text, for example, or Hebrew texts. Just as it is. If it doesn't, you can feel free to send me along error messages that you're running into, and I can see if I can help you walk through. I was the co-PI on a project on medieval Arabic literature. Sadly, I don't read Arabic, but I've worked with it in the past, and I don't recall too many problems that we ran into related to running through these files in right-to-left languages. That does not mean it doesn't happen. Okay, so we can actually see that ren only occurs in a few different texts. We can see it occurs in a few of the short stories early on in the collection, and then here's a story where it happens a whole lot. So, excuse me, this is kind of interesting. These labels are really difficult to read. Let's see. So more resources for Chinese text analysis or Chinese NLP. So a lot of the documentation for Stanza has a lot of useful stuff. Let me make sure you can see this graph though. Let's make that smaller. Let's see here, hopefully. The labels are illegible, but it kind of shows you where this term occurs across these different short stories. DH Quarterly has had a few journal articles on Chinese NLP. I've put out some stuff in Cultural Analytics. Donald Sturgeon has written a decent amount about Chinese NLP as well. I would check out the tools section on ctext.org. That's a good place, and I'll put this down here, ctext.org. What else is a good place to go? There are a lot of things being written on word tokenization, and you kind of just have to search for those. I am putting together a textbook on Korean, Japanese, and Chinese NLP that I hope to have finished at some point in the next, who knows, hopefully 6 months. We'll kind of see where that goes. It's still pretty early days on the planning for that. And I'll also post the syllabus to my Chinese NLP class, which I think would be perhaps a good place for resources there. As far as adding word position indicators, it definitely is, but it will require slightly different processing. So for example, let me close this and hide that. So for example, if you wanted to kind of keep track of where I suppose you mean where in a line a word occurs, perhaps. You would have to add it to your processing step somewhere. So you might divide, let's say you have a file full of, let's imagine it looks like this. So I have poem, 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 1, and it's, say, 4 lines. 1, 2, 3, 4. And then I have poem 2 here. That's something like this. So what I would need to do in a case like this is I would probably try to load each poem in individually. So this might be making sure that each poem is in its own file, or, for example, having some sort of header between the poems that's something like poem and poem. And that would be just fine. Whoops, I don't really need to save this. And so then I could split on these poems, and then I would have a list full of the poems. And then as I process these words, I would want to keep track of where in the line they occur. So it is a little bit complex, but it is absolutely doable. And this is, I think this is one of the really nice things about learning how to program, is really you're only limited by, I mean, technically what the computer can do, but generally speaking, the limitation is actually imagination and just figuring out the syntax to make it work, right? So all of these things definitely possible. But I think with that, I've now been streaming for an hour, a little over an hour in fact. Excuse me, 2 hours, wow. I think I'm gonna have to leave it here. My voice is starting to kind of go out, but I think look for other series in the future. I do think I'll do more streams on probably regular expressions, more advanced natural language toolkits, the natural language toolkit, probably more on SpaCy, and maybe a little bit more on advanced Chinese processing and talking a little bit about processing in other languages as well. But my hope was, out of all of this, that people who are interested in processing and doing NLP, who haven't ever done it before, could kind of get their feet wet. And if any of you out there are William and Mary students, I do run a digital humanities lab that is focused on student-driven research. And this series will hopefully encourage students to kind of learn everything you need to know to get started there. So feel free to reach out to me. I'm open to collaborations for research for William and Mary students. Unfortunately, I don't have the time to do too many other collaborations, but you know, who knows? Just drop me a line, and I'm always happy to at least chat. So with that, have a good Friday. Enjoy your weekend, and good luck with any projects that you have. And I'll see everybody next time. All right? Thanks again. This was fun. I enjoyed this, and hopefully you did as well. So take care.